So this is the lecture 5.3.2, focusing on the electronic heat capacities of solids, especially of metals, and the course is of course solid state physics. So what we will do in the upcoming lecture is that we will estimate what is the electronic heat capacity or electronic contribution to the solid's heat capacity, and realize that only few of the electrons nearby the Fermi level can actually contribute to the heat capacities. And this is the fact that explains why the classical Drude model fails so badly in treatment of heat capacities of metals, while the Dulong-Petit estimate for heat capacities is pretty okay even for the case of metals. So this is what we will learn during this lecture. So we can now estimate the electronic contribution to the heat capacity, to the total heat capacity. And in the previous chapter, we discovered how we can contribute the lattice contribution, how phonons also can absorb thermal energy and how they can affect to the overall heat capacity. But now we also realize that electrons can also have a contribution, and that's usually being denoted with CE. And this electronic contribution, most of the time, it's not very large, especially when we are at a moderate temperatures, so close to the room temperature. But as we noticed in our earlier treatment of the heat capacities, when we go to colder and colder temperatures, so to the cryogenic temperatures, then the lattice contribution vanishes quite quickly. So that when we go to the cooler temperatures, then the dependence on T dramatically decreases the lattice contribution to the heat capacities. And because of this difference, this contribution, the electronic contribution, then often starts dominating when we go to the cryogenic temperatures. So this is what happens, and this is what we will learn next. And we will not go into the very much into the mathematical details. We just provide a quick, crude estimate for the electronic contribution, and that will be enough, because our main point here is not the thermal properties anymore, but rather the electronic properties. We will need the heat capacities to estimate them, but we do not need to deal with the heat capacities in overall rigor anymore. We just are happy in the kind of first things that they need to be discovered regarding the electronic heat capacities. So only the essence, this description is that only the electrons that are nearby the Fermi level EF can contribute to the heat capacities. And how come that happens is that when the electrons are far away from the Fermi level, in essence, they cannot be thermally excited. And this is being explained in this picture, and I hope I can make it clear, so that when we are in these electron states that are not very close to the Fermi level, and when we are at a moderate temperatures, the kind of thermal energy that each of these electron states can take, it's not that much. So that the electron state could only move a few milli-electron volts upwards in energy by addition of the thermal energy that is associated with the temperature of the system. And then that means that only the electrons that are nearby the Fermi level EF, they can actually be lifted into a higher energy state by thermal excitation. And the most of the conduction electrons that are there in our piece of a solid, especially a piece of a metal, they do not really contribute to the heat capacities. And this is the fact that explains why with metals, the Dulong-Petit prediction is still pretty okay. Because even though we have many electrons in a piece of a metal, only a tiny, minuscule proportion of those electrons can participate into a thermal storage of energy, heat so in essence can affect the heat capacity of our solid. And now we can just estimate, this is a very a rough estimate, but we can estimate that the kind of number of participating electrons is of the order of kBt. That's roughly the kind of width of our Fermi level. Please remember in the earlier slide, we had the width approximately 4 kBt. So we're just assuming that this is width now kind of like the width of our Fermi distribution is now kBt. It doesn't really matter, is it like 2 times kBt or 4 times kBt, but just the kBt order of magnitude is okay. And then we must multiply that with the density of states, so that we can kind of estimate how many electrons we have in this area, in this width, and then that gives us essentially the area of the curve, and that essentially corresponds to the number of electrons that can be thermally excited. And then if we can estimate how many electrons or such electrons we can have, then we can estimate their effect on the mean energy. And please remember that the heat capacities were calculated by taking the temperature derivative of the mean energy, so that if you can estimate the amount of mean energy, then we have essentially solved the heat capacity and its electronic contribution. So we want to calculate the mean energy, and this is what we will do next. And in essence, please remember the equipartition theorem, so that each degree of freedom that is being associated, each degree of freedom is being associated with a mean energy of 1/2 kBt. And this is the equipartition theorem. Specifically, of course, it says that each energy degree of freedom that depends quadratically on some variable will be associated with this amount of energy. And the nice thing about the equipartition theorem, that it applies in an equilibrium system, so that it also gives us a tool to relate the macroscopic temperature of our system with the actual energies that we have, that we can then calculate how much of energy is being associated with a given temperature. But we don't need that. We just need to estimate like what is the mean energy. And since we know that we have 3 translational degrees of freedom, so that the electron can go anywhere along x, y, or z, then the mean energy can be given to be 3/2 times kBt times the density of states nearby the Fermi level times kBt, since we're dealing with the kind of thickness. So these terms here gives us the number of electrons, and then like this 3/2 kBt gives us the average energy associated with a single electron, and this density of states times kBt tells us how many electrons we have in the piece of metal. And then 3/2 because we have 3 translational degrees of freedom, so that the electron can move along x, y, z, or any direction associated with these different directions. So the electronic contribution CE now can then be estimated via its definition, so that we calculate the temperature derivative of our mean energy, and that gives us simply 3 times kBt squared times T times the density of states nearby the Fermi level. And this is now our heat capacity contribution associated with the conduction electrons. And please note the temperature dependence. It's just a linear temperature dependence that will explain how come at cryogenic temperatures this contribution becomes dominating. So the lattice contribution, CL, was of the functional form that it depends on the cube of the temperature. So essentially the Debye T cubed law. But here what we have solved the electronic contribution CE, and we see that really dominates at low temperatures, because the lattice contribution vanishes dramatically more quickly than the electronic contribution. And this result also shows the importance of the electronic density of states, so DOS, and of course the Fermi level, because they are in essence very important here in the calculation. We must know what is the density of states nearby the Fermi level. And here I'm showing what happens when we go to the colder temperature. So because the electronic contribution has a linear dependence on T, this contribution does not vanish as quickly as the lattice contribution that depends on the cube of temperature. So in essence, the phonons, they freeze out when we go to colder temperatures. And then when we would cool down metals to really cold temperatures, but I believe we should go to only to some tens of kelvins, then this lattice contribution becomes a dominating factor for the heat capacities. So this is what I wanted to say in this lecture. And then what we will continue next is that we will discussing the Wiedemann-Franz law. And then finally, we will go to the screening of the electric field that provides us a kind of like a justification why this free electron model is such a kind of like a okay model after all. So I thank your time and patience, and please, I wish you a good day. Thanks and bye-bye.